What we've talked about so far, we were talking last time about dimensional analysis. And of course, dimensional analysis is actually using dimensionless parameters to be able to say something about a system. The basic idea is that if you can take groupings of those parameters that have no dimensions, then you can build relationships between them, clever and insightful relationships between them, to be able to say something about how a physical system works. And so that has certainly been the genesis of what has been done in looking at pipe flow. And pipe flow, as shown here, we did some simple examples about what the dimensionless parameters were that would be the characteristics of pipe flow. And we skirted the idea that really Reynolds number is the critical parameter that we need to deal with, that indexes the kind of flow that we get. And this is a demonstration of that for flow in a pipe with a tracer die entered into the center of this pipe. And what's happening here is that the flow is going at different speeds. From early on in the clip, where it is laminar at relatively low speed, and you see a nice even bead going down the pipe. The velocity is increased and you get this little ripple effect going in it. So you have eddies forming at some locations, and a fundamental transition between those behaviors occurs as you increase the velocity, and the velocity is indexed relative to Reynolds number. And so what we want to do is we want to be able to say something about flow in pipes. It's kind of an important thing. If you look at, I think on the very first time we met, we looked at one map of the US that showed this absolutely dense network of natural gas pipelines covering the country, bringing what was natural gas up from the Gulf up to the heavy using states up in the Northeast where all the population is, storing some of it in Pennsylvania, for instance. I don't know whether you know that some of the salt deposits, subsurface salt deposits in New York State and northern Pennsylvania are used basically as repositories for that, so that when everyone turns their heaters on in New York City at 7 o'clock in the morning, there's enough gas to be able to supply that. So these are just drill holes pushed into the ground, water circulated to the bottom of the casing as the casing is pulled up, so you get these big, long, cigar-shaped caverns in the subsurface, which you put natural gas into, displace water, brine from that to the surface, and then when you want to get the gas, you just put the water back in, and it pushes the gas out, and it goes into the pipeline, etc. And so pipe networks are an important part of our life for energy, also in your public sewage systems, etc., the piping in your house, and so it's clearly an important component to deal with. So that's what we'll talk about for the next couple of weeks, I guess, to be able to understand exactly how that relates. So let's just skip back a little bit to reiterate our recap from last time. And so we made the point that when we look at dimensional analysis, there are these three things we have to accommodate. We have to have geometric similitude. The model has to look just like the real thing, and it has to include everything scaled down in the appropriate way. And so when we look at pipes, we'll also see that this transition from laminar flow, laminar meaning that the individual layers of water all just scoot across each other like pushing a deck of cards parallel to each other, to turbulent flow, where now all of a sudden it's no longer parallel and planar relative to each other. As you make the transition to higher Reynolds number, just like in a golf ball, which has dimples on it to be able to set up turbulence because it can travel through the air more efficiently, in pipes it's the small scale roughness on the walls of the pipe which heralds that transition from laminar flow to turbulent flow as the velocity increases. So clearly, if we're doing scale models of this, we have to also incorporate that roughness, which we'll find out. So geometric similitude has to be honored as the first requirement. And if we honor geometric similitude, then kinematic similitude is the next parameter. In other words, we want the velocities to be the same. And so in our case, that translates to being Reynolds number. A velocity a density, a length scale, and a viscosity as a number. And then if that's the case, then we can then use the flows measured in the model to be able to represent the behavior in the prototype by basically using Euler number in most of the cases we talked about. Euler number similarity between the model and prototype, and that is that the pressure generated or the stress generated is proportional to the density of the fluid and the velocity squared. And so that's typically the way that we'll look at the systems. So we have some very useful non-dimensional numbers for us to deal with. And of course, the non-dimensional number for this would be something like, we haven't labeled this, but this would mean that these ratios were the same in each of these models. Not, I guess this is the model, right? Not the prototype. And so those are the three requirements that we need to deal with. I won't talk about this. We did talk about, when we chatted about non-dimensional numbers, the fact that we could look at ratios of numbers, but we actually developed ours from a Bernoulli equation, right? So we had a gravity term, which is the z term, a pressure term, which is p over unit weight of fluid, and a momentum or inertial term, v squared over 2g, and also a viscous term, this h sub l term that we deal with as well. So we had those four terms. And from looking at ratios of those parameters, we came up with things like Reynolds number, which is the ratio of inertial to viscous forces. And so the other way to look at this is just to, instead of using Bernoulli's equation, just look at what the magnitudes of the forces would be in any of these terms. So we know that the inertial force is mass times acceleration. We know that the weight due to gravity is equal to the mass times gravitational acceleration. We could write Newton's law of viscosity, which we know is the shear stress is equal to the viscosity times a change in velocity with location, and we could multiply that by an area on each side to get a force, a shear force, just like this. So this is this. We can get pressure by taking a pressure and multiplying by an area. We can get a surface tension, which is newtons per meter, multiplied by a characteristic length to get a force. And likewise, when we talked about designing bridges so that they don't become galloping Gertie, as in the Tacoma Narrows Bridge, and self-destruct, then we can also look at aeroelasticity in structures and in planes, where the key parameter is the flexibility, the elastic modulus of the system. And so what we could do, in this case, we have 6 individual force terms. We could look at every single permutation and combination of those to be able to look at important terms. And so we could do the things that we did with the Bernoulli equation from maybe a raw standpoint, more raw standpoint, to look at the Reynolds number, which by definition is just the ratio of inertial to viscous forces. It comes out to be a characteristic dimension embedded in here. The Froude number, which is ratio of inertial forces to gravity forces, and also the Euler number, which is pressure divided by inertial forces. And so you can get a whole series of these terms, which we've said that the most important two for our cases are probably going to be Reynolds number, which is what gives us kinematic similitude, and the Euler number, which allows us to be able to relate pressures or forces applied on bodies to between model and prototype. But there are a number of others. I guess the first 3 here are the ones we've dealt with already up to this point here. The others that you'll have heard of in constant use are the Mach number, the velocity you're flying at relative to the speed of sound. The importance of that is that, the way that we dissipate energy from structures is the same way that you're hearing my voice here. It's the speed of sound. The energy that's coming from my larynx, I guess, and is being projected to you. It's traveling to you at the speed of sound. And so the significance of the Mach number is that if you're traveling at the speed of sound, then the energy that you're trying to dissipate from an aircraft or a flight structure can't physically get away. And so you can think about it as dropping, for instance, a pebble in a stream. If you drop a pebble in the stream, the ripples from that pebble after a certain amount of time will have traveled a certain distance. If the nose cone of your plane has traveled a small length of time in space after that, and it will have another ripple attempting to emanate from it here. So this is how far the energy would have traveled for the first ripple if it was physically moving through the system. So you end up with a Mach cone, which is centered on the tip of the aircraft, which was here at some earlier time, now is here at the current time. And inside this Mach cone, all of the energy that you're generating to push yourself through the air is being trapped in here. So you have to make flight structures that are much stronger. The analog, I guess, would be on a plan view of a ship traveling through water. It's trying to push a bow wave ahead. The bow wave travels at a certain rate, the celerity wave speed in our particular case. If you're going faster than that bow wave, then you end up with a wake because it can't physically get away from you faster than you're traveling. And so to be able to push the ship through the water, you have to actually almost surmount that bow wave to be able to move forward. And so you have to expend extra energy to do that. Other ones. I'm not sure we'll use Strohal number. If you are interested in flow of viscous fluids, multi-phase fluids, the Weber number is something that's close to being a capillary number. In this case, inertial forces over surface tension forces. Actually, I think the capillary number is what? It would be viscous forces over surface tension. So in other words, if you're trying to push oil through a reservoir through the pore throats, the resistance to flow is by viscosity because it drags against the side of the pore throats. But also the other impact is that you have bubbles of oil and bubbles of gas or bubbles of water in the system, which have an interface with each other. They don't mix with each other. They're immiscible. And so to move components through reservoirs, you have to be able to overcome surface tension forces. And so in very fine-grained materials, it's tough to be able to push things through them because the surface tension forces become very large compared to the viscous forces, and you can't. And a bunch of other things. People doing contaminant hydrology studies, Peclet numbers and Courant numbers. I'm not sure we need to be able to talk about those. So there are a variety of numbers that important non-dimensional numbers that define behaviors. All right. So how do we use those in what we'd like to look at now? So we made the point already that when we look at, let me go back to this. When we look at the behavior of a fluid, that if we want to be able to represent the behavior, we're going to have to look at three different requirements. That the model is correct, geometric similitude, that it's running at the right velocity. And so, in other words, we'd expect that we have to compute things at the right Reynolds number. And finally, that then if we do that, we can calculate what the forces are on the structure through something like an Euler number. And so what we'd like to be able to do is we'd like to be able to figure out exactly typical questions we'd like to ask is what kind of pressure do we have to add to the upstream component of this flow to be able to make sure it arrives downstream at some given velocity that we'd like. And so we have most of the tools available to be able to do that. But what we're going to have to account for is the fact that at different velocities, the behavior perhaps changes. And so we can look at a simple way of being able to describe this behavior. And of course, the simplest way is to use two things. We'll use the energy equation, which we talked about in week 8 or so. And we'll talk about the head loss terms that are embedded in that. And we'll try and figure out exactly what the appropriate magnitude of the head loss terms is. We know how to do it in a very simple way for laminar behavior because we have an expression for that. But we'd like to be able to do it for much more complicated behaviors, such as the ones that are shown in this pipe, which include this wavering flow, so the non-laminar flow we have in the system. And so that is what we would like to do. So let's start off with what we know about this system. So what we'd like to be able to do is we'd like to be able to build a pipe network of some components between an upstream location and a downstream location. We know that in here we could put in a pump, which might be a reasonable thing for us to have within our network. And if we do that, we know, for instance, that we can write the behavior as what? An elevation term, a pressure term, a velocity term, plus the amount of energy we have to put in to be able to pump it. And on the downstream, whoops, okay. And on the downstream side, we have the equivalent of each of these terms. So gravity, pressure, inertia, and also some sequence of terms which we've referred to as the loss. So pump energy into the system and sum of losses in the system. And so this ends up being our viscous loss term. All of these are in units of length. And so what we might want to do is figure out exactly what this term looks like in terms of what we think it would look like in terms of the appropriate non-dimensional variables. We also know that if we look at our system, we've talked about this a couple of times, that if we look at flow through a pipe, at least for the very simplest system, we have something characterized for some length, that we would drive this flow by a pressure drop over length. Here we would also have some appropriate material properties. So we have a dimensional description of this, so geometric similitude, which is d over L. We are going to try and get a kinematic similitude, which is probably going to be Reynolds number. And so we'll have d over L, presumably is an important parameter for us. Reynolds number may well be a parameter that's important for us. A velocity, a density, a characteristic dimension, any dimension, it could be L also, and a viscosity, ratio of inertial and viscous forces, and maybe something that looks a bit like an Euler number. And so we can see exactly how that would work out. So for the very simplest case, for the laminar case, and so we'll find out that laminar means for a Reynolds number less than, say, 1,000. We haven't justified that yet. That we can write a relationship that says something that the average velocity is equal to a diameter squared over 32 times the viscosity times the pressure drop divided by the length. And so if we know what the pressure drop is, we know the length of the pipe, we know the diameter of the pipe, viscosity, we can calculate what the average velocity is. And so this average velocity, you'll remember, I can't really get it in here, but let me draw it here, is if you're looking at the outlet of the pipe, the true velocity profile is this kind of parabolic profile with 0 velocities, top and bottom. And what we're doing is we're just making it assume that it looks like this, where the area under the curve of each of these figures, this parabolic figure and this prism, are the same. So the product of velocity times area, length across the pipe, is the same. So what we'd like to be able to do is be able to index this in some appropriate way. And so this term here is going to be an equivalent pressure drop that we'd have to apply to be able to get it through the pipe. So this is a pressure drop divided by a unit weight. So this is actually units of length. So maybe we can rearrange this expression in some way to be able to make it look like this. So if we're going to do that, we'd like to be able to write this expression as change in pressure. I'm just going to rewrite this expression in some way. So average velocity, and what's it going to be? It's going to be 32 times viscosity times length over d squared. We'd like it to be equal to this term here, so probably we can divide both sides by rho g. And what else? I can also write this as, I've done this before, so I know what I want to do. I can multiply it by 1, because I'd like to be able to maybe get a v squared term in here. It should be this. And maybe also multiply by 2 over 2. So I've done nothing to this other than multiply by 1s and rearrange terms. So now what we're going to do, let's gather some terms. This term is P over rho g, which is the same as HL, right? This is really what we're attempting to do. And it's a function of, we have v squared over 2g. We have 2 times 32, which is 64. We have length over diameter. So we got 32 is gone, 2 is gone, length is gone, d squared is gone. And the other term is velocity times density times d. So velocity times density times d, and we're left with viscosity on the top. And so if I rearrange that slightly differently, I'm going to write it as equal to length over diameter. It's going to be 64 over Reynolds number. This term here is 1 over Reynolds number, and it is v squared over 2g. And so this is the standard way that we will deal with this. This is the head loss. And so in other words, if we want to be able to define the expression that goes in this term, it's just going to be sum of the head losses are just going to be equal to 64 divided by Reynolds number multiplied by the length of the pipe divided by its diameter and multiplied by whatever the average velocity is. And this is the average velocity, right? So in other words, it's this term here. Okay? And that's going to be the fundamental expression that we use. Yep.
Why is it the head loss? I understand that you started with the average velocity, but how does it relate physically to the head loss?
It relates to the head. Well, it's not. It's the change in pressure that you get over divided by unit weight. And so it's this term here, right? To be able to drive flow from this upper stage here to this zero pressure, reference pressure at the other end, the pressure drop that you apply to be able to drive flow at that given velocity is just this term. And so the pressure that you need to be able to, so this is the pressure that you apply to be able to deal with this. This is the loss that occurs due to the velocity flowing at any given the fluid flowing at any given velocity. And I guess if you wanted to think about physically what it is, actually you could do you could think about it this way. So you have on this surface, instead of a velocity, you have a pressure here that's applied. You have on this downstream side a pressure P2 that's applied. The difference between those is P1 minus P2, and the force due to those is the difference between those multiplied by the area, right? So if you're balancing momentum, there is no change in velocity in this system because it's a constant section area pipe. So the velocity at this upstream end has to be the same velocity here, so there's no change in momentum. And so this has to be reacted against if we write our momentum equation as velocity times mass flow rate has to equal sum of the forces in x. So there is no change in velocity as you go. So mass in equals mass out, so this term would be 0. And so if you sum forces, the only force acting against this is going to be this. So it's going to be the shear force multiplied by area inside, and the area inside is going to be pi d 2 pi r, pi d times L. So this force here has to balance this. So it's just a balance of the forces that's lost due to frictional losses. And so it's equivalent to, it has to be equated to the pressure that's applied upstream. If you solve this as a Bernoulli problem, there would be no pressure drop in the system, right? Because there's no velocity change. Horizontal pipe, constant diameter pipe. The pressure up at the upstream part, if you ignore this term on the right-hand side, the pressure upstream has to be the pressure downstream if there's no viscous losses, because there's no change in velocity, so V1 equals V2. It's horizontal pipe, Z1 equals Z2, no H, and so the pressures have to be the same. The only way that which you can destroy pressure or use up pressure in this case is by viscous losses. So that has to be the outcome. Another question? I don't know if that answers. Yeah.
What are the units of
The head loss and length. They all have to be units, yeah. So if you look at this, Reynolds number is dimensionless, length over diameter is dimensionless, and we know the v squared over 2g term has to be the same as each of these, so it has to be length. So yeah, so head loss is by definition length. Yeah, Daniel.
You said if there's no change in velocity, there's no change in pressure.
If it's an inviscid fluid and there's no change in velocity, there'll be no change in pressure. And you can prove that yourself just by thinking about the Bernoulli equation. V1 and V2 have to be the same. Z1 and Z2 are the same if it's horizontal. And so the only possible term that could change is P1 and P2. And so if the left-hand side equals the right-hand side equals 0, P1 equals P2. Okay? Okay, so that's kind of a fundamental relationship for us. And so what we're going to find out is that now we know something about this behavior. And what we are going to do, what will color our activities from now on is, I'll move down one page. So this is an absolutely fundamental expression for us that we have here. It's no different from what we've talked about before. This is our energy equation. Written in one dimension, so it's Bernoulli equation. It's an energy equation because of a couple of things, right? This has to be upstream, always. This has to be downstream, just by our convention. This is the amount of head that gets put in by a pump or taken out as a turbine. They all have to be units of length. And these are what are referred to as major losses and minor losses. And I'm trying to remember which one is which. Yeah, okay. So minor losses would be bends and fittings. So faucets and bends in pipes. that may, and so typically these are just defined as the head loss is equal to some constant, a loss coefficient, K sub L, V squared over 2G. V is the average velocity in that fitting, typically. So you see that here. And the major losses are, in some cases, which we've just said is, was it length over diameter or diameter over length? Length over diameter, right? Sorry. Diameter, F, and V squared over 2G. So F is referred to as a friction factor. And this friction factor for laminar behavior is equal to, only for this one case we've looked at, is going to be equal to, for a circular pipe, 64 over RE. And so this is for only a circular pipe and only laminar flow. So we'll look at this equation many, many times before we're done. Lam in R. And so the consequences of this are that we could imagine drawing a figure, actually a very important figure for us, which will look like this. Bless you. And since we know that this loss is going to be indexed by three things really, I guess. The velocity of the flow in the system, which we'd like to know. Perhaps we'll know in some cases, perhaps we'll have to iterate towards it in other cases. It's going to be indexed by the length of the pipe to its diameter. So if we double the length of pipe, we'll double the frictional loss. If we quadruple the length of pipe, we'll quadruple the friction loss. So it scales with that. And whatever the magnitude of this friction factor is. So a very important parameter or figure that we'll use is called a Moody chart. After someone's last name rather than after their attributes, I suppose, or their demeanor. And that is that the friction factor plots as a function of Reynolds number and is typically shown on a log scale, but it will have a curve which is F equals 64 over Reynolds number. And that's exactly what we've shown from our previous working. But what it will also do is it will show, this is for laminar flow, and this is for turbulent flow, and maybe this is 2000 in terms of Reynolds number. And so we have this behavior now, which we know what to do with, but we've made this point that it's really only for the simplest case that we could imagine. And the simplest case is where we have laminar flow, the deck of cards. One laminae of water sliding over the other one, so that when you look at the behavior in a cross-section of a pipe, then you get this parabolic behavior. So in other words, as a consequence of viscosity, the velocity on the edge of the pipe is anchored at zero velocity. If you go next to it, it goes a bit faster. Goes next to that, it's a bit faster, until it's fastest in the middle, and then it recedes off to the back. So that's the simplest way. Laminar comes from that terminology. What we don't know is what the behaviors are here. And it'll turn out that we end up with a bunch of lines, and we're kind of jumping ahead of ourselves right now. And we said that if we only have two pi groups, we would have a unique expression. So if pi 1 was equal to the friction factor, and pi 2 which is Reynolds number. So this is a velocity, a diameter, a density, and a viscosity. If this was our second pi group, then we just have one relationship which would uniquely define our whole system. It turns out that once we get into this turbulent regime, beyond, say, a Reynolds number of 2000, then all of a sudden we get a whole bunch of other relationships. And these relationships are magnitudes of epsilon over d. And so epsilon equals roughness, and d equals diameter. Of the pipe. And so we can also kind of rationalize that that should be the case as well. And so we don't have a particularly simple system. We've shown through our very simple use of this flow equation for pipe flow that the magnitude of this major head loss, it's a very small head loss, but it's major because it's over the whole piping system. So if you have 3,000 kilometers of pipe going from the Gulf up to the northeast, then it's a very small loss per unit length of the pipe, but over 3,000 kilometers, it's a big number that you have to overcome with a pumping power in the system. And so we could rationalize the fact that it's a function of v squared over 2g. I suppose what we could also do is we could go back to our discussion of Buckingham pi and figure out exactly how we would end up getting this particular chart. And so let's kind of do that. So let's go back to Buckingham pi. So we made these three comments. We have to have dimensional similitude, has to look the same, exactly scaled model. If it's then kinematically similar, we have a chance of being able to do something about it through the Reynolds number. And then we can measure some other parameter, such as the Euler number, that will describe our system. And so what is our minimum system going to look like if we believe that we have this? So it's not very different from what it was before. It has a diameter. It has a density and a viscosity, which define behavior. It has a pressure drop that occurs over its length, which is the energy we have to put in to be able to make it move along the pipe. Anything else? We're missing one other thing, right? So epsilon is the amplitude of this roughness. Sorry? Epsilon is the amplitude. No. This is the pipe. The example we showed before had this little wiggling component, but the observation is that transition from laminar to turbulent is set off by the roughness of the surface. So in other words, if you took this and you looked at the surface of the pipe would look like this. And it's this height here, which we'll always call epsilon. And that will describe our system. And so what does Buckingham pi tell us? What did we call them? We called them, I'm trying to think what, I don't know. Well, we called them variables, right? So what did we had change in pressure is some function of what? We have a velocity. Which is really describing the system. We had material properties of density and of viscosity. We have a diameter of the pipe. We have a length of the pipe. And we have now a roughness. And so, do we call them K and R? K terms are the number of terms we have. So we have 1, 2, 3, 4, 5, 6, 7. The R terms are mass, length, and time. Which ones of those do we have represented? Mass, density per unit volume, so for sure we got mass. Length, well, I've got lots of terms with length. And velocity for sure is length over time. So we have all three represented. So this is equal to 3. So the number of pi terms is going to be equal to 7 minus 3, which is 4. And so what are those terms potentially going to be? Well, actually, what will those terms be? They could be, for instance, we could do it just by guessing. What would be the guesses? Let's lay them out this way. Dimensional similitude. My writing's getting worse. Kinematic. And dynamic. So I'm not going to go through Buckingham pi and develop them, but you can imagine that the terms, we could just actually pick them out by inspection. So what's kinematic similitude going to be? You know that. A velocity, an average velocity, a characteristic length, it could be d or l, or it could be epsilon, it could be any of them. Turns out by doing experiments it works out that it's d, but it could be any of them, and you can always relate them to each other. Density and viscosity. So that's one of the 4. Dynamic similitude. Well, it's going to be the forces on a structure. So it could be the Euler number, but it could also be equal to the term that we've used here, and that is that it's really this length here. And I guess it can't quite be, it can't be delta p over unit weight, because we know that this has units of length, right? So it has to be something else. So it's, I guess it's going to be something like the Euler number. Let's take it as the Euler number for now. Change in pressure over rho v squared. So those are 2 numbers we've got out of this. What else do we have? The others, let's do it the other way. And so we could go through Buckingham pi to get them, or you can also do it by inspection. If you can pull out numbers which are satisfy the requirements of being completely filling up the set of variables. We've used every single of these parameters, hopefully. We've used pressure, we've used velocity, we've used density, we've used viscosity, and we've used all of the characteristic length dimensions. So we've satisfied the requirement that within these 4 non-dimensional parameters, we've used up all of the parameters which describe our system. So we're honoring our system. And we've ended up with 4 parameters, all of which are non-dimensional. Reynolds number is non-dimensional, Euler's number is non-dimensional, and by definition, these 2 extra parameters we get out of the system are also non-dimensional. So if you cast your minds back before, when we dealt with this problem, what did we do? We didn't worry about the fact that we had a roughness, and in the problem statement, the length parameter was included in delta PL, right? It was pressure drop over length. So we really had just one parameter here which already incorporated this length. And as a function of that, we came up with delta P over L, it had a D on the top. So instead of having the 2 pi parameters that we had that time, an Euler number and a Reynolds number, which absolutely defined our system, Now, because we've added 2 extra parameters, we've got 2 extra pi terms. So instead of just Reynolds number and Euler number, we have 2 other parameters that define behavior. Length over diameter, because we've kind of decoupled this pressure loss term and added this length term on the left-hand side. And also relative roughness, because we've said that this is an important function of creating turbulence in our system. And so the behavior now that controls our system is going to be defined by these terms. And so if we want to be able to, I know it's getting a bit crowded here, we want to get the head loss terms. It's going to be a function of the length of pipe divided by its diameter. It's going to be a term which is a friction factor, and it's a term which is the inertial head, if you like, v squared over 2g. And so what this is saying, this is basically the equivalent of HL. It's not the right units, obviously, but because this is units of length and this is unitless. This index is flow. This length over diameter term is included in here. And this friction factor is going to be a function of this relative roughness in our system, which we have defined as this absolute roughness magnitude. So in other words, it's fractions of a millimeter. It's the roughness that's on the edge of the wall. If it's a plastic pipe, it'll be nice and smooth, and therefore epsilon's going to be very small. If it's going to be a cast iron pipe with threads on the inside, epsilon's going to be quite large. And so that's what we'll use to be able to do this. And so just to show you that we're not just kind of plucking things out of air, we'll maybe, let me zip on here to show you this chart. This is exactly what we're going to be dealing with. And so really what we've done is for ourselves, we've rationalized how we can come up with some chart that defines what the loss is of energy on our pipe system. In other words, what we have to overcome by putting extra energy into the system by pumping. And we've defined it as a function of Reynolds number. This is 1,000. This is 2,000 right here. This is the term that we talked about that we derived for simple laminar pipe flow. And we see that as we get faster and faster velocities, then depending on the kind of pipe we have, if it's a very rough pipe, then we get a transition to turbulent flow occurring quite early at a low Reynolds number. If we have quite a smooth pipe, we have a transition to turbulent flow occurring quite late. But from these, we should be able to basically define what this head loss is. And so what we're going to do is we're going to be able to calculate what the head loss is as a function of the length of pipe to its diameter, its friction factor, and how quickly fluid flows in it. So this we can look at. It's going to be, we know how much gas we want to deliver, and so we know what the velocity is that we'll want to have in the pipe. We know how long the pipe is. We could figure out how large the diameter would be to be able to accommodate that flow. And if we know that, then we have everything now we need to know to be able to say, if we know what the roughness of the pipe is relative to its diameter, we know what the velocity is at which it's flowing, then we can calculate what the magnitude of this friction factor is. And that's really what we're doing. So that's what we'll spend the rest of our time doing. We just have to understand where this comes from. So again, dimensional analysis, incredibly powerful technique. Only very simple geometries can we get analytical solutions for, which are these laminar flows in very specific pipe cross sections. If we want to deal with real flows, then we actually have to do experiments to be able to figure out what the dependencies are. But dimensional analysis can guide us in that to be able to give us the correct kinds of expressions and to guide the experiments we do. So all of these lines that are shown here are experimentally determined. You take a pipe of a given roughness and you start flowing fluid along it, and you just measure how much pressure drop you get as a function of the velocity that you apply in the system. And because we know that this dimensional analysis boils down to the minimum number of parameters, we don't have to do the experiments for every single diameter and roughness of pipe that we have. We can choose one diameter pipe and we can do it for each one of these roughnesses and get each one of these curves, which is how that's done. Okay. All right, so I'm going to leave it there. So we'll spend some time doing that. And you can see, I guess, the challenge of this is that the things like Reynolds number is a function of velocity and also the dimension of the pipe. And so because things like the amount of fluid that we want to push along a pipe and also the diameter of the pipe are a function of the Reynolds number, we may have to iterate to get a solution. We can't always get a straightforward solution. If we know what the flow rate is, immediately we know the Reynolds number, we uniquely know the friction factor, and we can solve in one step. But if, for instance, we want to calculate what the flow rate would be for a given pressure applied on a pipe, we might have to iterate to be able to get a solution. And so it's not so straightforward. Okay. So I'll leave it at that. Thank you.